Broadcasted or? Okay, I see the countdown.
Yeah, I'll say a few words first.
Okay.
All right, well, I hope people are still joining. This is going to be a great session. We've got 4 great speakers who've got some really interesting work to share with us. Each speaker has about 15 minutes. We'll have a few questions we can take after. You're also welcome to please put questions in the Q&A tab, and the speakers, time permitting, will orally repeat those and answer the questions after their talk. And if not, they can type their answers later. So with that, let's go off to Sebastian, and let's have you be our first speaker, Sebastian. Go ahead and I guess you're already sharing your screen. We're good to go. Thanks.
Okay. Yeah. Thanks a lot, David. And hello, everyone. Yeah, it's a pleasure to present this work on collapse. Yeah, which has started almost 2.5 years ago, and which has really become something that I never imagined it could become. That being said, this presentation is really an academic presentation, and I won't be able to complete it. I plan to do actually an alternative recording on it, which I'll make accessible. For now, I think I'll just give you a broad overview of collapse and then cherry pick things from the presentation, but I won't go into the examples because I won't make it with the time. So what is collapse? To try to break it down in one sentence, it's a C++ R package that facilitates statistical computations of high complexity at outstanding levels of performance and programming efficiency. And it does that in a way that integrates more or less seamlessly with popular classes and data manipulation frameworks in R, like Tibble or Data Table. And it also fully supports the efficient infrastructure we have in base R, like matrices and factors and so on. So to give you a bit more detail about that, what kind of infrastructure does collapse provide? So first of all, it provides a large set of statistical functions and operations that are C++ based and that are vectorized along multiple dimensions, notably along columns and groups, including weighted statistics and statistics for categorical data like modes and so on. Collapse has enhanced time series and panel data support, which includes indexing of panel data and time series, native handling of irregularity, advanced transformations such as scaling and centering, and exploration of panel data, for example, panel data autocorrelation functions and so on. It has some recursive operations on lists of data objects, which I won't really cover here. And it has some advanced descriptive statistics tools like weighted cross tabulations and so on. It has some data manipulation programming and utility functions, which includes quite fast routines to group and order data and to determine unique values. And which is really the most recent development, it has data transformation by reference and OpenMP multi-threading, which is an area in progress. So the way Collapse provides these things is also quite unique because it really aims to be a class-agnostic package, which is implemented through S3 generic statistical functions and quite intelligent object handling. So I can confidently say that Collapse fully supports base R, all the objects we have in base R, and it also fully supports most of the objects most people deal with, like TS, XDS, Data Table, Tibble, SF, and so forth. Collapse is very, very efficient, and I could say that the C++ powered computations scale almost linearly in data size, regardless of the dimensionality really of the problem, in particular the number of columns and groups. The R code of Collapse is also very strongly optimized, so all functions on a typical machine execute below 50 microseconds, which really changes the way you can write programs. There are many internal optimizations, and users can also access many C++ level algorithms and helper functions in R. The API is stable since more than a year, and there are some API extensions, which I might cover briefly. And what is important really is that Collapse was designed from the start for socioeconomic data, which is data with many missing values. So the default for all the statistical operations in the package is to skip missing values, and it works reasonably benevolent on groups, say, where you have all values, and it also was designed to support and preserve variable labels and various other attributes attached to data. So the core piece of, or one of the core pieces of infrastructure of Collapse are these S3 generic fast statistical functions.
Ooh, it looks like we lost Sebastian's internet connection. We'll give him a minute or two to get back on. Yeah, let's give him a minute or two to get back on. I really would prefer to try to keep pretty close to the implied schedule so that if somebody wants to jump in and catch somebody's talk, they're kind of catching it at about the right time. Do you guys have any other suggestions? Paul, Michael, Hadley?
Should have prepared a discussion topic to chat about.
I think it's reasonable to give them a chance to reconnect.
Yeah, give them a few minutes. Yeah, it's your opportunity to show off any special skills you have. Can you juggle, Paul? You must have some kind of trick, Paul, I feel like.
Well, Hadley, can I put you on the spot to have you tell us what's new and exciting at RStudio that's coming down the pipe?
So many secrets I'm not allowed to tell you.
Hey, how about no secrets? Just anything that we're not aware of that has been announced.
No, I'm just overloaded with secrets right now, so I can't say anything in case I spell the wrong secret. But I know we're already excited about RStudio Conf. One thing people might not have heard about is that JJ has been working on his Quarto, which is kind of the next generation of R Markdown that's really been built from the ground up with multi-language support. So it's R and Python and JavaScript and whatever we need to add in the future. So it's worth checking out if you're an R Markdown user, I think. If you're an R Markdown user, obviously, if you're an R user, maybe the Python stuff isn't that interesting, but it's just like a bunch of kind of things that we have learned about the R Markdown and the ecosystem that are now in Quarto. So Quarto is like R Markdown plus Blogdown plus Bookdown plus some other down I'm forgetting about, but it kind of has everything bundled in and a lot of like just really thoughtful things. Just one of my favorite is, if I can find it, it's just like a lot of kind of thought has been put into like if you want to do like multiple figures side by side or code blocks side by side, and then that works for HTML and PDF LaTeX as well, which is pretty nice.
Actually, I used it for my presentation yesterday. I thought it was quite nice.
Nice, yeah. I mean, it's kind of like if you're an R user, it's like, yeah, it's nice. It's cleans up a few rough edges of Markdown, Markdown. I think if you're like a Python user, it's like pretty, there's sort of a, I think it's been pretty hard to kind of do the sort of like scientific publishing in the Python ecosystem. It's certainly possible, but it's a lot more work than Markdown made it. So it's really kind of cool to bring that to a wider audience. Yeah, what else? Other stuff. Yeah, I've just been working a lot on Conf, which I probably shouldn't be flagging a user up, but it's in DC at the end of the month. And now it's going to be in person, which is both exciting and a little scary, I think. But it's going to be so great to like see people in person, and hopefully not get COVID.
For those of you just joining us, we lost our first speaker through a technical glitch, lost his internet connection. So we're going to give Sebastian a few minutes to get back on. In the meantime, you're welcome to ask questions of Paul and Michael and Hadley while we wait a few minutes for Sebastian to get back on.
I will tell you one of the backup, we've made these probably excessive backup plans if one of the speakers gets COVID at our StudioConf, and one of the layers of the backup plan is if you're too sick to present, I will do slideshow karaoke of your slides. So I will present your slides sight unseen for you if that is an option that you would like. So.
And perhaps you're joking, Hadley, but I could say that for those people interested in Sebastian's talk, he did post the PDF of his slides on the right-hand panel. You'll be able to click that and download his slides.
My Safari just crashed, but hopefully.
Our next speaker is whoever is connected.
Just do speaker roulette, whoever's up for speaking.
Yeah, Paul's next. Let's give let's wait a minute or two in case someone's trying to catch Paul's talk. Let's give him a minute or two.
I lost the unmute button. Someone's asking in the chat about Spatial Sample, which was our new release yesterday. Wow. Which I'm going to totally drop in the chat very casually, but it's a new package for spatial cross-validation that plugs into the rest of the Tidy Models framework. So if you are a person with spatial data who does a lot of modeling, a lot of cross-validation, can't say anything bad when Hadley's on the line, yeah. I will say one of the funnier things, we do the advertising and it's my highest liked tweet ever, like 500 likes on Twitter, but I didn't link the GitHub, and so about no extra activity on that as a result. But yeah, I think it's a very cool package. It plugs into everything you expect it to plug into, and if it doesn't, please let me know.
All right, Paul, why don't you start your talk? Let's do that. Next speaker is Paul Morell.
Right.
Go ahead and share your screen. We got a minute.
How's that? All right, good to go.
Yep, looks good.
Okay. Thank you. All right, so this talk is about, I want to describe some things that have been added to the R graphics system in R4.2. And I want to start with a little demonstration. So this is a little Shiny app. I haven't written many Shiny apps, but one of the things I recently discovered is that Shiny will let you react to mouse events on the plot. So what this little Shiny app does is whenever I hover over a point, it redraws the plot and draws a tooltip on the point that you're hovering over, which was good fun for me to play around with. I've been able to do that before, so that's what this Shiny app does. Now, the cool thing about this app is that these are the things that Shiny can let us do. But what I want to focus on today is that tooltip, the less interesting part of the app. Okay, so the difficult part in terms of our graphics was drawing that tooltip. That's a close-up. Now, there are some details about that little tooltip that you might not notice the first time around. So I'm just going to point them out, some little features of it. First of all, you can see through the tooltip. So you can see through to the points in behind. It has a little shadow that's got a funny shape to it. And you can see through the tooltip, you can see through the shadow, but you can't see the shadow behind through the tooltip. So the shadow is a really funky shape. So there's these things about that tooltip. Okay, now what I want to do is try and draw it. I'm going to try and draw that tooltip and use that to demonstrate some of the things that are new. Okay, so starting with just drawing using what already exists, let's suppose I've got a little function here that draws that tooltip shape. What I'm doing here is I'm just going to draw the tooltip initially, or at least just the shape itself, fully opaque. So I'm drawing this. And that's just basically a polygonal shape. It's not completely trivial with this little thing down here. I can explain how to draw that later, but it's basically fill a shape, draw the outline of the shape, and then draw some text on top. Okay, now one of the features that I want in my little tooltip is that I want it to be semi-transparent. I want to be able to see through it and see the points behind it. So here's the simple way of doing that. This is again existing stuff. So I can just dial down the transparency of the thing I'm drawing, or the colors that I'm using to draw. So the fill is going to be see-through, and the border is going to be see-through, and I get that, right? So now I can see through the tooltip. But there are some subtle little problems with that result there. And again, you might not be able to see it first time around. So what I'm going to do is just point out some of the issues. The text on that tooltip that I just drew was a little bit redder than it needs to be. It was a bit redder than the border, and the border actually had sort of 2 levels of transparency going on. So here's a little blow up of the tooltip I just drew, and this again is with just the pre-existing graphics sort of stuff. So I'm drawing a shape. I'm filling the shape with a light pinky color, and I'm drawing the border with a reddy color. Both of these are semi-transparent, but I have this problem where the border overlaps the fill. There's I'm seeing through the border and then through the fill and then whatever's behind it. And then where the border doesn't overlap the fill, I'm seeing just the border and then whatever's behind it. So I get this icky sort of artifacts in what I'm drawing. And the same deal applies to the text that I drew on the top. I see through the text and then through the central part and then through the fill and then through whatever's behind it. Okay, so just going back a little bit, that's why there's these little artifacts going on. And this text here is actually a bit of the wrong red. Okay, now, if you're like me, it's a bit of a nuisance. So what I want to show next is, well, how would you do that properly? How am I want to draw what I want using some of the new things that you can do in graphics? Okay, now this is not a completely new thing from 4.2, but it was new in 4.1. So a thing we can do when we draw from 4.1 is, rather than changing the individual colors of what I'm drawing, I can set what we call a mask. So here I'm defining a mask up in this part up here, and that mask is full of a semi-transparent color, and then I'm putting that mask as part of a viewport. So basically there's a context for drawing now where everything that gets drawn will be, because of the mask, will be made semi-transparent. That's old news. The new thing in 4.2 is that I can draw what I'm calling isolated groups. The idea with a group is that you describe a bunch of stuff that you're going to draw, and that stuff gets drawn together first and then gets added to the picture. And what I'm doing here is, this is my tooltip shape. Then and note that I'm drawing the tooltip opaque, okay, just like I originally did. But then I'm drawing the tooltip as a group, and I'm using the viewport with a mask. So basically that says there's a context where everything I draw is semi-transparent, but I'm drawing this tooltip as a group. So the tooltip gets drawn, then the mask says make it all transparent, and then it gets added to the page. And that's the result. Now, if you've got very good eyesight and an excellent memory, you will notice differences between this one and the previous one because the artifacts are gone. So the text now is the same color as the border, and there are no funny little double transparencies on the border. And that's because of this fact that the tooltip was drawn completely opaque first, and then that final result was made transparent and then applied to the page. Okay, so that's one thing that's new in 4.2 is that you can draw groups sort of essentially off screen and then add the result at once. So that's the real blown up version of the new result, which is now beautiful to some eyes. All right, so the other part of the tooltip that I was drawing is that shadow. Now, it's pretty easy to make just a gray version of the tooltip shape. Okay, that's what I'm doing here. Fill it with gray to make the border gray. Same shape as the tooltip, just gray. So the second new thing I wanted to show is that when we have a group, what we can do is we can define the group and then use the group separately. Okay, so we don't have to sort of define it and use it all in one hit. Now the point of this is that what I'm doing here is I'm defining this gray shape, and then I'm changing the context in which I'm drawing the shape, and the context is half the height of the context that I defined the shape in. So when I use it, it gets shrunk. So that's the shape shrunk down by half, because I defined it in one context and then used it in a context that was shorter. And another thing I can do is, because essentially what we're doing is when we're using a group as a separate step, we're potentially applying a transformation to the group. I can add extra bits to that transformation. So for example, I can share the, let's not share it with my friends, but push it sideways, as well as shrinking it or rotating it or whatever. And so in this case, I define in one context this shadow shape, then I define a new context that is shorter, so it's going to squash it. And when I use the group in the squashed context and I apply a shear transformation as well, then it gets pushed off to the side. And so that's creating that sort of weird shape that we started with. The third thing that you can also do in 4.2 is with these groups again, is that when you're drawing these groups separately before you add them to the main image, you can combine drawing using non-standard operators, compositing operators. So what's going on here is I have two bits of drawing. This is going to get drawn on this source is going to get drawn on this destination, and there's a operation being described as to how those two things should be combined. So normally that operation is just over. So when you draw a second thing, it gets drawn on top of the first thing. But this one says when you draw the second thing, wherever you overlap the first thing, erase the first thing. Okay, and so I'm drawing the original tooltip shape on top of the skewed off to the side shape, but using a clear operator. So wherever the first one overlaps with the second one, as shown by the dotted line there, it removes the second one. And so that's the very strange shadow shape that we got at the start. So then, of course, if I apply a mask to the thing that I'm drawing, to that group of things that I'm drawing, I can make them semi-transparent. Okay, so that's then the complete tooltip. We've got a group that is being drawn opaque and then added to the image using a mask, so that the whole tooltip is semi-transparent and see-through, but in an even sense. Combined with another group that was squashed, sheared, had another group drawn on top of it to remove bits of it, and then drawn with a mask onto the page. And that's what made the pretty tooltips in the demo. So that's happening every time we hover over a dot. So these are some things that you can now do in graphics in 4.2. There's a slight caveat, because these things are only implemented in some of the graphics devices, but there's a few of them, so there should hopefully be one that works for you wherever you are. And what's it for? Well, that's not my job, that's your job. So the main idea really is that there are now sort of detailed graphical outputs that you can produce that you couldn't produce before, which if you were wanting to already do that sort of thing, now you can do it. So your frustration is at an end. And if you didn't want to do it already, then one of the useful things about having these additional tools is that maybe you can start thinking about drawing stuff in ways that you hadn't thought of before. Okay, thank you very much.
All right, thanks, Paul. Let's take a few minutes. Are there any questions for Paul? You can unmute your mic, or maybe Paul, looks like there's one in the Q&A tab. Could you just...
Yeah, I'll read out the Q&A one, right?
Yeah.
Okay, so the Hadley asks about the color of the mask, or does the color of the mask matter, or is that just is it just the alpha channel? And the answer is it's just the alpha channel. So the mask, this mask, right? So the mask was defined by, it's a rectangle that is filled with a semi-transparent black, and all that's being listened to is the alpha channel. So that could be in a semi-transparent red or white or whatever. There's also a on some graphics devices, there's what do you call a luminance mask, where the semi-transparency of the mask depends on the grayscale of the color, not on the alpha level of the color. So there's two ways of doing the mask as well.
Great. Other questions for Paul? I guess one question would be, what's next in 4.3?
Well, depending on how well the second half of the year goes, one of the plans is to take a look at the font support in R, which if anyone's ever tried to draw any text at all, it's a bit of a mess. And Thomas Lynn Pedersen has done some pretty cool things with the RAG or RAG package. And so we're going to have a chat and see whether we can get some of that stuff into the main R graphics engine.
Well, great. Let's give a little bit of time to Sebastian, who got cut off for an internet problem. And Sebastian, why don't you take about 5 minutes if you want, or less, and just give us some of the highlights of your package. Sorry, we got you cut off.
Yeah, sorry. Let me try to share my screen again. Yes, first of all, sorry for the internet issue, but I think it's a positive sign, because I'm definitely going to make a much more detailed recording of this presentation. And I'd really, I think, like to maybe just stress some of the computational possibilities of Collapse. To just show you some benchmarks here. For example, you can see at the bottom of this slide where we aggregate 10 million observations over 1 million groups. And you can see that the first expression is really like a simple aggregation, which takes about 9 milliseconds on a single M1 Mac core. And if I aggregate that with a pre-grouped data set with 1 million random groups, we can do that in 13 milliseconds, which is a substantially lower overhead than a data table currently at the group level. Although Collapse cannot be parallelized at the subgroup level, but it can be parallelized across columns. And if I show you another example here, using input-output matrices, which are of dimension about 5,000 times 5,000, which I aggregate in 300 groups. And I have 32 matrices here for basically a global value chain analysis. So aggregating those matrices with Collapse, which amounts to 45.7 million sums and 2.6 million, can be done with 4 cores on an M1 Mac in 0.3 seconds, which is a huge increase in computing power available to our users. And Collapse has similar contributions to the time series domain, which it supports fully indexed data frames and vectors, which handle irregularity in the panel dimension. And also the computation speeds here are well in advance of basically any other time series framework currently available in R. And it remains for me to really point you to the documentation and also to the website. So Collapse has a built-in documentation. If you install the package, you can just call that directly from R, and it will basically, just reading the main page will already give you a very good idea of what Collapse is about and what it can do. And yeah, you can have different topical pages. And there's also a nice website through GitHub, which is this one here. Again, sorry for the inconvenience, and yeah, I'm going to do a proper recording of this presentation and share that either through user or privately through YouTube or through the Twitter channel. So you're gonna have that, and yeah, I hope still I could give you a glimpse at least of what Collapse is about.
All right. Thank you, Sebastian. Fantastic. Yeah, thanks for giving us a quick overview of what we've got, and we'll look forward to seeing what your longer talk. Let's jump over to Hadley as our next speaker. Hadley Wickham. Hadley, I think you're still muted.
Thank you. Hey, everyone. I'm Hadley Wickham, and today I'm going to give you a first look at a new OOP system for R. So while I'm talking today, I'm talking about work that's been done jointly by the R Consortium Working Group on Object-Oriented Programming. And I'll talk a bit more about this group and with it later in the talk. But to begin, I wanted to talk a little bit about, like, well, why do we need object-oriented programming in the first place? And to kind of motivate a little bit, I've created this Bizarro function. And the job of the Bizarro function is basically to take a vector of various types and like turn it upside down, put it into Bizarro world. So for example, if it's a numeric vector, it flips the sign. If it's logical, like if it's false to true or true to false. If it's a character, it reverses the letters in the string. If it's a factor, it reverses the levels, so on. And so you can see here with just these sort of 4 types, it's pretty manageable. But you can imagine if I added more and more, had to handle more and more classes or types like dates or date times or ordered factors, this function is going to get longer and longer and more complicated. But more importantly, there's only one person who can add to this function, and that's me. So if you have created some new type of object, you'd have to come to me and say, Hadley, can you add another if statement to this function? And as you can imagine, this is like really important for functions in base R, like print. Like print has to be able to deal with just about any type of object you can imagine. And if this was all going to be in one function, first of all, it'd be huge. It would have hundreds or maybe even thousands of if branches in it. But more importantly, like if you created a new object and you wanted it to print specially, you'd have to go and bug RCore. So the goal of OOP systems is to try and work around this. And R has two key object-oriented programming systems already built in. The first one is S3, which was, as the name kind of suggests, developed for the version 3 of the S programming language. S3 is basically the simplest possible OOP system you could possibly imagine. It's just built of a few fairly simple conventions. And after S3 had been around for a while, people started to see, like, it's just so simple, it's got some problems. So they came up with S4, which is the object-oriented system designed for the 4th version of the S programming language. And S4 kind of went very far on the other. It was very formal and rigorous and had a lot of power. But as hopefully this picture is suggesting, just like Goldilocks, S3 was a little bit too simple and S4 was a little bit too complex. And the goal with R7 is to find something that's just right. So the name is really meant to imply that we're taking the best parts of S3 and S4, adding them together, and we're designing something specifically for the R programming language, not S. So what does R7 look like? Well, first thing we're going to do is load the R7 package. So currently, R7 is just a package on GitHub. We hope to get it to CRAN in the near future, but the long-term goal of R7 is to get it baked into R itself. So this is something that you eventually won't have to load a package for. But we need to do that for now, and then I'm going to create a new generic function. And the idea of a generic is just a function whose behavior depends on one of its arguments. In this case, X. It depends on the type of thing that you give to X, if it's a data frame or integer or a character or a function or whatever. That's basically what a generic function means. You're going to have define some interface that talks about how the function works, and then we have a bunch of implementations for different types. So the first argument to new generic is just the name of the generic. You'll notice there's a little bit of duplication here because we're also going to save that to a variable. That's going to be our function, Bizarro. We considered another number of options to avoid this duplication, but in the end, decided that this was the least worst solution. And then we're also going to just give the name of the argument used for dispatch. We're just going to call that X again here. So this defines the implementation. So this defines the interface. This function doesn't do anything yet. What we next have to do is provide some implementations for different classes. And we provide implementations by registering methods, which we do with this new method function. So method takes two arguments. The first is the name of the generic, and the second is the class. And here I'm using classes or types from base R, like numeric and logical and character. So these are all built into R7 itself. So this first line says I'm going to add an implementation to the Bizarro generic for the numeric class, and that's just the same implementation as before. I'm just going to reverse the sign of that number. Similarly, I can add a method for logicals and for characters. And now that I've done all that, I could take another look at this Bizarro object I created. And when you do that, you'll see, when you print that, you'll see that this is an R7 generic. It has 4 methods. So you might wonder why there are 4 methods. We just added 3. That's because I kind of lied to you, or we lied to you a little bit. Numeric isn't really a class in base R. It's a combination of integer and double. So R7 takes care of that for you and automatically adds a method for integers and a method for doubles. But this print method, so also all of these things that look like R code actually is R code. So if you copy and paste those and back into the console, that will let you get that method or that implementation of the generic for that specific class. So if you're familiar with S3 or S4, this is just like one of the small conveniences we've baked into R7. You can print a generic and you see what all the methods are, and you can easily access those methods as well. So now we've defined those methods, we can start to use our Bizarro function, and it behaves as you expect. If we give a 1, we get -1 back. If we give a true, we get a false back. And if we call it with some type of object that we haven't defined, we get a nice error message saying, well, this generic can't find a method for that type of object. So we haven't defined a method for functions, so obviously our generic function is going to complain about that. Now, there's kind of two parts to an object-oriented system. The first, or the style of object-oriented programming that we mostly use in R. First of all, we have generics, which basically define the behavior, and then we have classes, which define the data that each object is going to have. And so in R7, you can define a new class by, surprise, surprise, calling the new class function. You give it the name of the class, and then you give it a list of properties. So this is going to return a thing that represents the class. It's also what you're going to use to construct objects of that class as well. So it's both a class and a constructor. So here I'm creating a range class. It has two properties, start and end, and I'm saying both of them should be numeric. So I'm just having something that kind of defines a range of values from a start and end. So now I can construct an object with a start of 1 and an end of 10, say. I can print it out, and just the default print method just gives me the values of the properties, start and end. And as this print method suggests, if I want to access or modify those properties, I use this @ symbol, which might be familiar if you've used S4 before. It's very similar to the $. You've used a lot in base R. The main difference here is that the @ sign will only access the properties that you define. If you do anything other than start or end here, you will get an error message saying that you're trying to access an undefined property, whereas the $, by convention, just returns a null. You also see if we try and assign, we said that these had to be numbers. And so if we try and assign a character vector into that property, we get an error as well. So R7 gives you some basic kind of guarantees that an object you get of this type is going to have the constraints of that type. Now, of course, you can still construct range objects that don't make sense, where like the start is bigger than the end. R7 has a solution for that called a validator. So a validator is just a function that takes an object and it basically just returns an error message if there's something wrong with that object. So you could say, I want to make sure that start and end are both length 1 and that start should be less than or equal to end. So if any of those things aren't true, I'm going to return a string, and then R7 will automatically turn that into an error message for you. The other cool thing that you can do with R7 is you can create dynamic properties. So these are properties that are calculated on demand. We have to have a little bit more syntax here. I'm going to generate a length property, which is just the difference between the end and the start. So I create a new property, and this is going to be a read-only property that's computed on demand. So I'm going to compute that value with the getter function. If I also wanted to make this function writable, I could also use a setter function. And this is a pretty important part. I think this is a really nice feature of R7, because this means if you need to change the internal structure of your object for whatever reason, you can add kind of deprecation layers, so it's not going to immediately break other people's code. Now, if when I talk about maybe there's like problems with S3 and S4, and we're going to solve those problems by creating something new, whenever I think about that, my mind immediately turns to this XKCD comic, where it is very, very difficult to solve an existing set of problems by adding something new, because now you're just adding like a new thing for people to select between and a new thing that has slightly different conventions. So we are taking a bunch of approaches to try and make sure R7 is successful. The first of these is that R7 is fundamentally a team effort. So as I mentioned before, all of this, the work that's gone into R7 is the product of the R Consortium Working Group on Object-Oriented Programming, which includes representatives from R Core, from Bioconductor, from R OpenSci, from the Tidyverse, and from other interested members of the R community. So this isn't something that's just come out of like my head or one other person said, this is a team effort that hopefully will be adopted by many different communities. We've also taken, I think, the best parts of S4 and kind of ported them into a simpler, slightly simple framework. So we've kept this nice formal definition of class and properties. This is pretty important, I think, because it gives you guarantees that when you have an object of a specific type, you know exactly what that behavior is going to be. S3, because it's so informal, it gives you relatively few guarantees. You can do all sorts of crazy things to S3 objects that then when you are programming with those objects, you have to kind of carefully defend against. So we've tried to adopt kind of the formalities of S4, these clear definitions, where they make sense and where they think they'll make your life easier. Another thing that we've done in R7, which goes against basically every other object-oriented system and every other programming language, is that we've kind of embraced the idea that the users of these objects can reach inside and grab data out. And this violates a normally pretty important property of object-oriented systems, which is this idea of encapsulation, that an object is kind of a black box from the outside, that only the owner of the object kind of understands how it's implemented and can get data out. But and S4 tried to do that, and I think ultimately it didn't succeed because R is fundamentally about a language about data. And if you can't access the data you want deeply nested inside some object, you get really frustrated and you will do whatever you need to do to get that data out. And because R is such a flexible language, you can really do that. So rather than trying to fight against that, we've embraced that. The other thing that's really important is we've focused on backward compatibility with S3. So R7, you can just easily, if you're using S3 already, you can just do a drop-in replacement very, very easily. And we're working on improving the backward compatibility with S4. And then finally, because I've contributed a lot to this project, there's very much an idea of a pit of success, that you don't have to strive to succeed. We want you to kind of succeed by default. And the way that we achieve that is a lot of thought and error messages and documentation. So hopefully we point you in the right direction. And then if you're slightly off, we give you a clear error message, which will hopefully get you back on track. So we'd love for you to try it out. The website's there with the documentation for the package, and you can install the GitHub package if you want to give it a go. We'd love to hear what doesn't work, but we'd also love to hear what don't you understand. The documentation is definitely a big part of this package because we want people to be able to pick it up and understand why you might want to use this. And if you read it and you are left shaking your head and having no idea what's going on, please let us know so that we can do better. Thank you.
Great, Hadley. Really interesting stuff. You've actually got several questions in the Q&A tab. Maybe you could read those out loud and then give us some good answers.
Sure. So let's take a few of them. Let's go. So for Neil asked, how will these work with namespace? That's basically TBD. I think we have some ideas currently because it's like a package and not hooked into base R yet. It won't use the namespace. It does sort of various magic with on-hook stuff, but we'll expect that will change at some point in the future. David asks if R7 supports multiple dispatch. That's when more than one argument is used to pick the method. It absolutely does. It's not as central to R7 as the way that multiple dispatch is to S4. It's in there basically to support the kind of arithmetic operators like plus and minus and divide. But you can use it with any number of functions if you need to. It also uses kind of like a greedy algorithm rather than considering the full graph of method generic combination. So it's a little bit simpler, but pretty sure it'll be just as useful in practice. Conrad asks, will objects constructed from classes pass on by reference or by value when used as arguments in function calls? Kind of neither. They behave just like regular R functions, so they are kind of passed by reference until you attempt to modify them, at which time a copy is made, so that the object passed into the function is not modified by reference. We might consider some extension to R7 in the same way that R6 extends S3 and reference classes extend S4. It's not unreasonable to ask if R7 should have something similar built on environments. That's something that we have thought about but have not put any work into yet. There is no, John asked if there's any intended relationship with R6. R6 is a different style of object-oriented programming, which R7, so it's quite different to R7. And R6 has these very strong constraints around performance, which I think would be very difficult for us to match. So I think R6 will remain around for a long time, but maybe the use cases become a little more specialized. What else? Brian asked if there are any inheritance relationships among objects. No, but there are inheritance relationships among classes, just single inheritance, though not multiple inheritance like in S4. And then Charlie asked about the speed of R7 dispatch. There are benchmarks on the page. I can't remember where we are currently. The goal I think the goal is to be as fast or faster than S3, definitely to be faster than S4. But at this point in the game, we're mostly thinking about how do we make something that's usable and good enough to encourage people to switch from S3 and S4 rather than about performance. Did I miss any? Oh, is it already possible to use in an experimental package? Yes, I think it would be interesting to. I think yes. No, I mean yes, it is possible. No one has done it yet. You would be the first one, so almost certainly you discover some problems. But I think that is roughly where it is today. And the goal is like once we get some more feedback to get it out onto CRAN. Once it's on CRAN, obviously, very much possible for you to build packages on top of it.
Great, Hadley. One last question about eventual timing on CRAN release. And then with that question, we'll then move on to Michael.
I would hope we're on CRAN in the next 3 to 6 months. It's hard to know how much we haven't really quite figured out. We've got some steps in place, but we haven't fully worked out what the base integration is going to look like. So it's going to be a while. But the idea is that the package will always be, I think the package will always be available on CRAN, because that way, like tidyverse packages, which we want to support both the current and the last 4 versions of R, we will need a CRAN package in order to do that, since we won't be able to use it in base R. So I think we have to figure out how those are gonna live side by side. We'll work on it and we'll figure it out.
All right, great, Hadley. Fascinating stuff. You have a few other questions maybe you want to answer offline or answer typing. But let's let Michael Mahoney give his talk. Thanks, Michael.
Yeah, thanks. Let me pull up slides real fast. Hopefully that looks to everyone like it looks to me.
Looks good.
Awesome. Yeah, so thanks everyone for being here. I'm really excited to talk about Unifier, a unifying API for interacting with Unity from R. Before I do that, I should probably introduce myself. My name is Mike Mahoney, and I'm currently a PhD student at the State University of New York College of Environmental Science and Forestry. And my work really focuses on how we can try and help people understand large-scale systems, especially natural systems, things like forests. Because if you think about these sorts of systems, a forest happens across an entire landscape and over the span of hundreds of years. It's a size system that you can't actually experience from start to finish in the span of a single human life, which poses a lot of real challenges because we've done a lot of really bad things to this world. And so we have to make decisions about what we do with our landscapes, with our forests, and so on, that we won't be able to watch the outcomes of in the span of our own lives. And so, what my research group is focusing on is how we can use environmental visualization as a way to try and help people build intuitive understandings about these sorts of large scale systems so that we can have more informed management decisions going into the future. And specifically, we're looking at ways that we can use things like virtual reality and video game engines to do that. So, just two quick examples. Last year, some people in my lab put out this paper using tree modeling applications and game design software to simulate tree growth, mortality, and community interaction, where inside of this game engine, the Unity video game engine, they made this virtual forest that's on screen here. And because it's in a game engine, they're able to skip through time and show people how trees compete with each other for resources. And so inside of this virtual environment, you can watch trees that are more successful grow into the canopy, reproduce, form the next generation of the forest, and ones that are less successful eventually die off and get excluded from future generations. You can skip over time and start shrinking the system into something that better fits human brains. And similarly to the skipping over time, we're also looking at ways that we can help people skip over space. So I had this paper last year, Interactive Landscape Simulations for Visual Resource Assessment, where the idea with this one is that in the center of this image, what the arrow is pointing to is this little red dot. And these lit up areas in the landscape are its view shed. It's the areas that can see and be seen by that dot. And by bringing this into the video game engine, we can take view sheds, which are a pretty old algorithm. They're in pretty much every GIS software that you're going to download. We can take it and make it so you can interactively investigate the outputs of that model and start getting an intuitive understanding of how topography and visibility interact. If there's an area that you don't really believe your model's results, you can go out and so long as your camera's at the right height, so long as your terrain heights are real, you can walk to that space in the landscape and see why the algorithm believes that it is or isn't in the viewshed. And so both of these examples are built using this game engine, Unity. And Unity is an extremely popular video game engine, especially for smaller game studios. And if you're a game developer, it does pretty much everything you want it to. But as someone who's doing research, not game development, I've got some challenges. So Unity is a really complicated system. And that's because it's doing something really hard. It's complicated for the same reason Photoshop's complicated. But that means that it takes a long time to learn how to use. And if you want to do anything in an automated fashion, you have to write C# code, which is not something that most scientists do as part of their usual work. So Unity exists outside of the normal system of scientific tooling. Kind of related to that, it also doesn't really speak scientific data. If you have things like raster data for terrain elevations or imagery that you want to include, Unity doesn't know how to understand that, and it definitely doesn't understand more abstract things like polygon and point data. And last but not least, Unity is not really built with reproducibility in mind. You figure that if you are a game designer building an environment for people to experience, you are very intentionally handcrafting that environment. You're trying to force a specific sort of experience on the user. And it's really rare for you to tear it all down and build it back exactly the same way, so Unity isn't built for that use case. But that means that if we're running research in this system, building environments in this system, it's almost impossible to actually replicate our environments exactly unless you get our actual environment from us. It's something that all of the little decisions involved in building aren't captured anywhere. So last year at USAR, I got to speak about our first stab at trying to solve some of these problems with an R package called Terrainer. And Terrainer does a lot of different things. It's a client for downloading data from the United States Geological Survey's National Map API. It has some 2D visualization stuff in it. But in my mind, the core of the package is that it provided a first stab at ways to get spatial data into Unity from R. And so I'm not going to go too deep into the code here, but this is some basic Terrainer code, which will get a centroid for Zion National Park out in the southwestern United States, download spatial data for an area about 8 kilometers centered on that point. And then this last function, make manifest, takes the elevation data and imagery that this script downloads and turns it into a format that you can then bring into Unity. And so the output of Make Manifest is a bunch of files that it created in the format Unity's expecting and some C# code, so that just by pressing a button, you can get this fully instantiated terrain inside of the game engine. And this was a big step forward for us. Before Terrainer, there really wasn't a way to get imagery onto these terrain surfaces. It was pretty much impossible. And we can now visualize things like polygon point data on the terrain surface as well. But there's still some obvious drawbacks, even with Terrainer. So, for instance, one of the big reasons for using the game engine is the interactivity and the physical rendering. So, we want to be able to have people dropping into the scene and walking across the terrain surface. But with Terrainer, if you want to do that, you had to add it in Unity yourself, probably writing some C# to do it. If you want to add things on top of the terrain, like trees, buildings, 3D models, you also had to just do that yourself. So, since last year's user, I've been working on a package to try and address some of these problems called Unifier. And as the talk title says, Unifier is meant to be a unifying API for interacting with Unity from R. The idea is that Unifier should provide all of the low-level plumbing needed to have a connection between R and your code and the video game engine. And so the way it does that is Unifier provides these two types of R6 objects, the first one being what I refer to as a prop. And so from the user's perspective, they're writing code that looks like this up here. They're writing pretty standard, pretty idiomatic R code, where you're calling functions like add light, which will add a light to a virtual environment in the Unity engine, and they're changing how that light acts through standard arguments, light type equals point. On the back end, Unifier is taking all of that user input and capturing it in this R6 object, specifically down in this parameter slot of this object. And that's where all of the user level configuration options go. It's then going to, when we go to actually create this environment, use a function that comes with the prop that's called build to turn all of that user provided parameterization into generated C# code. But again, if you're using Unifier to create an environment, you don't need to know about any of this. You're writing what looks like normal R code, and quietly, secretly behind the scenes, it will turn into C# code automatically for you. So as you're adding all of these props to your environment, so you're adding things like lights, 3D models, terrain, they're all getting stored in the other main type of object that Unifier uses, which is a script. And the primary job of a script is to capture all of the props that you're adding and the order that you're adding them in, so that when we go to actually render the environment, Unifier can just step through the props, generate C# code as necessary, and then execute it all at once. And the really cool thing about the script is that it actually lets props, as they're being added, look and see what else the script is doing and change their own behavior or the behavior of other props in order to write more efficient code. So you figure, for instance, doing things like adding 3D models involves a lot of standard boilerplate with a few different configurations depending on if you're adding a building or a tree. Well, if you're adding a prop that can look up and say, oh, there's all of this other boilerplate I can take advantage of, then we can write shorter C# scripts by just reusing those code chunks, those methods elsewhere, which results in simpler, shorter, and more efficient generated code at the end, which I just think is really neat. But so once you do all this, you add your props, you specify everything you want in the environment, you call this last function action, which walks through the script, converts all of your user provided R code to C#, and executes it inside of the video game engine so that you wind up with these fully rendered environments, no clicking involved, no C# on your end involved. And this is what that looks like in practice. This script creates a Unifier script object. It adds some terrain. This is just a procedurally generated bumpy terrain to that environment, adds 100 random trees to random positions on that terrain, then adds a light, saves the scene, and renders it. And I really want to stress that even though this is turning into C#, it looks like R. You shouldn't have to need to know C# to build these environments. And by running this, we wind up with a fully rendered environment in the game engine in an entirely reproducible manner. We're now expressing these environments in something that we can throw into version control. that we can attach as an appendix to a paper that we can make available so that people can reproduce and replicate our experiments in a way that hasn't been possible before. And that's been really exciting for us. The other really exciting part of this is that Unifier is built to be built on top of. So if you recall, this is the Terrainer code that I showed a few minutes ago, which downloads a bunch of spatial data and turns it into something that you can then bring into Unity yourself. Well, Unifier is now on CRAN, which means that Terrainer is able to provide a new function, Make Unity, which handles all of that for you. So now instead of getting a bunch of files out of Make Manifest and having to deal with the import yourself, we've gotten rid of even that amount of button clicking, where Make Unity will now render this landscape for you automatically. And the really cool thing is that because it's extending Unifier, it works with a lot of the functions that Unifier is providing out of the box. So we can take that new Make Unity function and add some code from Unifier. So add default player here adds a player character, a camera that you can control to the environment. And now we can create those interactive environments entirely from R. We're getting to a point that you don't need to be writing any C# or clicking any buttons at all. So that's Unifier, and I'm really excited for it to be public. Our future plans for the package is we're planning on wrapping a bit more of Unity's API so that you're able to do more from R without having to touch C# yourself. And we also specifically want to make it easier to generate landscapes procedurally in R and bring them into Unity, because there's a few tricks right now if it's not real world spatial data that you're working with. But mostly, I'm really excited to start using this so that people doing this sort of research can start doing it in a more open, reproducible way. So that's about my time. I want to thank you all for listening, as well as ESF's Pathways to Net Zero Carbon project for funding support. I posted the link to slides in the chat, and you can find me on everything at Mike Mahoney 218. Thanks.
Thanks, Mike. That looks fascinating. It certainly would be intimidating, I think, to jump into C# programming for someone that doesn't do that, but it's nice to access it directly from R. Let's see. Let's see if there are any questions for you. Yeah, I don't see any questions. Any questions from the other speakers?
I see one in the chat of how are video game developers receiving the concept. And I think it's one of those things of there is a real mismatch between the tooling that game developers are expecting and the tooling that scientists are expecting. So you think of things like Microsoft Flight Simulator, for instance, which is rendering the entire Earth and attempting to be as realistic as possible while it does it. When you're dealing with that sort of scale of real world rendering, going through R and actually getting the data into R is its own big challenge. So I haven't seen a lot of overlap between the approaches that people take for that sort of problem and the approaches that we're taking for things that are a little more scaled to your area of interest, basically.
All right. Well, thank you all, Michael and Hadley and Paul and Sebastian. I think those are fascinating talks. Looks like there's a lot of really good work going on, and we look forward to seeing the future. Thanks everyone else for attending. I think our session's over.
Thanks, David.